Just about there. Welcome back, everyone. And it is official. Looks like we can get started. So today's class, we're finishing off section 5.3, doing a couple more examples in that section. We're going to be using the 68 to 95 99.7 rule, the empirical rule, to approximate some computations using the normal model. We mentioned before last class that the rule of 5.3 is actually not too huge in this class. It's kind of a setup type section. The major thing we want out of 5.3 is what does the picture look like when you go to use a calculator to calculate those actual percentages, or you could say probabilities, exactly. So 5.3 sets up the picture. We'll do some computations there, but not a lot of emphasis. And we'll do a big emphasis on how it all goes when we want to do it more precisely in 5.4. So in both sections, we're using the normal model. And this is just kind of, I guess you could say, the warm-up section to all of that. I said my quiz 5, I wanted it to be off section 5.4, but that's just going to depend on where we end up today. I want to make sure we complete this section entirely before I release a quiz on it. So my quiz 5 might be a different topic, but if we get far enough today, we might be in section 5.4. Aside from that, quiz number 4 is going to be due next class. That's the one using the 5-number summary, the IQR rule of thumb for outliers, and then drawing a box plot and commenting on it. So that's where we're at so far. We're doing pretty good pace in the course so far. We might be about, I think, about a day and a half behind the syllabus, but that's okay. We'll make it work out in this semester. Our exam is still a ways away, so probably when we get closer to the around Friday of this week here, I'll start posting the information for the second exam. At midterm week, there's no special midterm project, there's no midterm exam or anything like that. All I'm going to do on midterm week is tally up what your score looks like for everything in MyLab statistics, all the quizzes. You're only in one and only exam. You can see your course grade here, your course score. I just report what that is on midterm week. So it's just kind of like a halfway check-in. But any questions at all, folks, with where we're at so far? Okay, so let's return back to this really busy diagram here and lots of information. This was kind of a rough page to end class on Monday night, right at the last part of a very late night class because there's so much going on here. So the refresher is if we look just to this portion right here, if I can zoom into the right amount, looking into just this amount, all we're focusing on is the so-called empirical rule. I usually say it as the 68, 99, 95, 99.7 rule, where 68% is the center two values. 95% is going from -2 standard deviations to +2 standard deviations. That just so happens to split up in this kind of nice and easy way, where there you go 34%, 13.5%, and so on. 99.7% of all the observations go from -3 standard deviations, which is quite far, all the way over here to +3 standard deviations. So that takes into account almost all the data. But this information only works if we're looking at sample data that is at least roughly symmetric, unimodal, or you could say mound-shaped as a synonymous way to say that. I put here approximately symmetric instead of roughly symmetric. If all that's true, then this normal model does a pretty good job of saying where your data lies. But we're going even beyond that. Once we have the data, we know everything we need to know about the data very, very precisely. All the observations are just looking at us. The histograms say precisely where they go in certain regions. But what we really want to do is take that summary data and say, this is somehow characteristic of the underlying population. So if my summary data is like, say, 100 Idahoans, maybe it has something to do with maybe number of credits completed in higher education, something like that. We want to use that sample data to say something not just about the sample, but describe the entire population of Idaho. So that's where the other interesting information comes into play down below here. If we're talking about populations, we're referring to parameters now. Statistics describe the sample. So on our little breakdown over here, we have a parameter on the left. That's the Greek letter mu. So This is read as mu, if you had to just write it out without the Greek symbol. That symbol down there is the Greek letter sigma, read as sigma in that way. If you had to write it out, that'd be a decent way to write it. On the left here, the Y bar and the S are statistics. In fact, we also often say Y bar is the sample mean, always saying the sample part, because we need to be very specific. It's the statistic, not the parameter mu. Parameters that describe the population are mu, the population's true but often unknown mean, and the population's true but often unknown standard deviation, sigma. So those are the parameters here. These are typically unknown unless we manage to take a census of the whole population and calculate those two values. So what we're doing here is we're taking summary data. This is the stuff we have, Y bar and S, approximating the parameters through what we found in the sample, and then plugging them in here, building up the normal model. So that's kind of a lot of leaps of logic in a certain sense, but does that make sense on how it all comes together? Okay, so suddenly it's really important how you get that sample. We like randomization. We want the sample to be representative. We'll look into some topics along those lines in around chapter 10. Now, there's some interesting terminology that goes along with mu, sigma, and the normal distribution. The normal model could be just referred to as an uppercase N if we wanted to. Then we could put in parentheses to say that model has parameters mu and sigma. So for just a really quick example using that pretty packed notation, you could say N. Let's just put in a number for mu. Mu could be, for some problem, maybe a 7.3. Number for sigma, almost any number goes, except it's got to be a positive number that describes how spread out the data is. 0 technically qualifies for sigma, but that won't fit a normal distribution. If you have quantitative data with sigma 0, that means every observation is exactly the same. That's like the most boring distribution in the world. All 100 people in the sample, for example, would have the same value. Maybe it's 12, whatever that number we're referred to. So usually that's a positive quantity as well, say 3. So this whole statement, N 7.3, comma 3, means the population can be modeled using the normal distribution with mean 3, standard deviation, oh, and I got that backwards, sorry, mean 7.3, and standard deviation 3. So it's just a really big paraphrase. Sometimes the sentence does just fine, but later on in section 5.4, if we're going to draw a quick graph, we might often tag that graph with N, the right value of mu, right value of sigma, just as a really quick way to paraphrase information. And that's helpful because that's information that goes directly into your calculator. So just writing that down is organizing all the information at once. Well, there's another distribution called the standard normal model. Nothing too special about that. In the standard normal model, all that implies is the mean is mu, which is 0, and the standard deviation is sigma, which is 1. It's standard in the sense that if we were going to write down a table of values for the normal distribution, that would be a good one to start with. And then you could use z-scores to translate from other distributions to this one. That's how people worked really hard with the normal models back in the day. But we're going to skip that kind of step and really just use a calculator to work with any normal model whatsoever. Our calculator just freely accepts both mu and sigma. So we'll take a feature of that functionality. We'll take advantage of that feature, I think is what I was trying to say. So what we want to do is put all this into practice in the example 2 down below. I guess I kind of gave up part of the problem by highlighting those. But here's what the context is overall. We're told the time it takes a driver to react to the brake lights on a decelerating vehicle is critical to helping avoid rear end collisions. So they give us a statement of fact, but mainly just to help us think about what the context is here. Feels like we're in a driver's ed class or something like that from that statement. But this is based off a real study that was done in 1993, so kind of old data. The article, Fast Rise Brake Lamp as a collision prevention device. So maybe something to do with building better brake lights is what it sounds like. But in that study, it suggests that the reaction time for an in-traffic response to a brake signal, so imagine you're on 17th Street, person in front of you brakes, we're wondering how long did you react to that and begin braking yourself? That braking time can be modeled with a normal distribution. So they collected a lot of data and found that it must have been reasonably symmetric, at least roughly symmetric, unimodal, so a normal model fits it. And the statistics in the data was 1.31. That would have been their sample mean. And a sample standard deviation of 0.42 seconds would have been the statistic for S. So it was sample data. They did collect statistics. But what we want to do is take these statistics and now use the normal model. So we're going to now specify the approximate values of the parameters. We're essentially doing this step right here. We're doing the approximations ourselves and now modeling a population, all drivers and their brake time reactions using, when it says state the values of parameters, there'll be mu is one. We want to use the appropriate symbols because they show up again, so we're trying to build muscle memory when we're putting them in the calculator. Mu is always referring to the mean, so I should have highlighted that part as well. It's just the mean of the population, 1.31 seconds. And there's two parameters. There's the mean and the standard deviation for the center and the spread. Sigma is the standard deviation for the population, 0.42 seconds. That's a weird looking sigma, but it doesn't have to be perfect. That looks a little bit better. So this is oftentimes kind of the more confusing question you might see on either a quiz or even an exam question. But this is all we're doing, taking the information of the problem and writing it down below. It's also a way for me to give partial credit because if we got them backwards or we grabbed the wrong number in a more heavy context problem, I would see what you indicate those two values as, and I'll check your numbers against them. So it's like, if you said this was 0.42 and this is 1.31, all the prompts here are going to be wrong, but I'll base my partial credit on those two numbers that you stated. So that's the start of the study. I think this is going to deserve a new page really quickly here. Now that we're actually modeling the population of everyone's braking time to brake light they see in front of them, we're going to draw the actual normal model itself. So this is the step where we're using the 68, 95, 99.7 rule. And it's going to look about like this. So start with a big horizontal axis, kind of like if you were doing a dot plot or if you were freehanding a histogram. On this axis, you want to put in what the quantitative variable actually is. But the mean value is a brake time of 1.31 seconds, and same with the standard deviation. That's your quantitative variable. I'll just say that this is reaction time to a brake. How did they say it? They said brake signal. So now the task that takes a certain bit of artistry, but you don't have to be a perfect artist for, is to try to draw this curve right here. The things that could lose you credit on this is if you draw something that goes, say, like this. So we could lose points on that because one key fact about the normal distribution is it never even touches the horizontal axis. It's always above. So we have to make sure our curve is floating above it. You also can't draw anything like this. It's a smooth curve. You can't cut yourself on it. Imagine it's kind of like a roller coaster. If you built this roller coaster, then you're going to send people flying. You want it to be a gentle, smoothed out curve. So it's got to look something about like this. I'm going to try again. I just wanted to draw some things that look a little bit odd. I would give this full credit if this is your sketch. But this is really weird because it decreases rapidly. It never actually comes back up. If we kept on drawing like this, we could lose some points because now it looks really, really weird. It never comes up in that extreme way. The curve that we're trying to write down as best we can looks about like this. Something like that. Again, it doesn't have to be perfect. If you go to draw it out, and this is a real exam, and you draw something that goes kind of like that, that looks a little bit weird. Let's maybe say that could lose a point. If your curve looks something like this, I would be okay with that. I mean, it doesn't have to be perfect. It just has to be rounded out at the top. Shouldn't have anything too extreme going on here. Should be above the horizontal axis. And the more we practice, the easier this gets. I think it's easier to draw it if you go kind of fast. If I draw it slow and try to overthink it, it comes out kind of funny. I'll just go with that. There's my curve. Actually came out kind of okay this time. Usually it looks a little funny unless I draw it a little faster. It's supposed to be totally symmetric, but any asymmetries you put in there, as long as they're not too extreme, like something that could go like that or like that, you'll get full credit for drawing out that curve. Next thing we need to do is label it, showing what the 68, 95, 99.7 rule predicts. The first thing we want to do is, this is meant to model unimodal data, so there's going to be a main peak if we looked at this as the histogram of the raw data. And that would correspond to where the mean of the sample is. Our mean just happens to be 1.31 seconds. So we put that down on the display. Okay, next, we have to decide on the scale. We want to go 3 standard deviations to the right, 3 standard deviations to the left. And the way you get those numbers is, well, pretty important too. We can't go this far for our first standard deviation. The first standard deviation is, if you look really close at this, notice that around here, it's starting to fall really, really rapidly right around here. And maybe here is about where the curve is the steepest. But once you go off to a certain point, it's no longer falling rapidly. It's kind of like a gentle descent somewhere out here. There's a transition point between the rapid fall and the gentle descent. If you're curious of what that's called, it's called an inflection point. The point of inflection is where we transition from falling rapidly up down the curve to falling gently. And you don't have to place it perfectly, but it would be right about there. But in other words, another way to think about this is you're just trying to match up the shape of this right here. That's 1 standard deviation right about that location. You're trying to capture the central 68% of the data, in other words. So if you put a tick mark about there, but maybe you move this slightly to the right, I'm not going to be super picky. If you move this slightly to the left, that would be a little bit weird, but I wouldn't be super picky on that as well. It starts to look weird if you put it way out here. That looks way, way off. Or if you threw it, say, way far to the right as well. That would be not quite what the rule is trying to say. So let's bring it back to roughly about here. This is where we get to use the calculator finally. This tick mark is 1 standard deviation away from the mean, which just means we add 0.42 to it. So go 1.31 plus 0.42. So that would give us a value of 1.73. I have to write kind of sideways because I kind of scrunched it together, even with writing big. Then you just do it again. Try to maintain the width of this interval here. Put in another tick mark to the right. In the calculator, you know you could just go plus 0.42, and that does it right away for us. Go plus 0.42, and it saves a lot of typing in there. That's going to be 2.15 seconds. And then another deviation to the right. My curve didn't quite go that far, so I'll just sort of draw it in a little bit further. Go plus 0.42 again. And let me fix that 3. There we go. And we're at 2.57 seconds. So those are all the values going to the right. And just for a quick idea on the notes, we took this and add sigma equals 0.42 repeatedly to get all the values. Does that make sense to folks so far? Awesome. So we're building up the normal model for this population, and we do the same thing going to the left. So this will be 1, 2, 3 tick marks going to the left. Start at the center once again, 1.31. This time, you're just subtracting 0.42. So go minus 0.42. Keep in mind that this is the negative sign, so you have to literally use the minus here on the far right of the pad. This will be at 0.89 seconds. It's good to remind yourself what these are. These are reaction to break signals. So these are people who are really very twitchy. They're reacting extremely fast. Subtract 0.42 seconds again. This would be a 0.47. Maybe this people around this range are slightly paranoid and they're just ready to break. Subtract 0.42 again. And this starts to become really unusual, 0.05 of a second. Way out here, these might refer to people who practically have some kind of second sense. Maybe they knew someone was about to break and they were just about to break themselves in anticipation. But you know, the thing that's weird about the normal model is there might not have been any data out here. The data might have been from here to here, for example, but the model still extends off to the left in that kind of way. So the model isn't fully accurate. It's just an approximation of what the summary data was doing itself. And we're using that approximation to approximate the population as well. So that's an approximation on top of an approximation. And even worse, we're using parameter values, or it came as approximation from the statistics themselves. We can't say how reliable that approximation is. A lot of this work feels kind of sketchy, but that's part of our goal. We'll find a way to show how reliable putting mu in for y bar really is when we get into content such as confidence intervals later on. So we started by drawing the curve, setting the scale here with all those values. Next thing we want to do is actually say what this rule right here predicts by putting in percentages. There's lots of ways you can do this, but for the sake of computation, parts C, D, and E below, it'd be a good idea to kind of break it up like this. I have a little border. The center is the 68% for the 68, 95, 99.7 rule. But if I break it up even finer, 34% goes here, and that's just a slightly more convenient number for us to work with. Then the next number, hard to kind of remember, I was reviewing them before class just to make sure I did, is 13.5%. I need arrows next to show that goes in. Then it's 2.35%. And the one that we actually calculated at the top of the notes is, on this last extent to the right of 2.57 will be 0.15% of the population. This is the population that's going to take more than 2.57 seconds to respond to a break signal. So these are the people who might rear-end you possibly in this kind of traffic situation. So if you can get the numbers going from the center to the right, you just reflect them going to the left. The curve is 100% symmetric. So in this region, it's 34% again. In this region, it's 13.5%. In that region, 2.35%. And the final small region here is the 0.15%. We add up all of these percentages, it'll come out to 100%. So we've accounted for everyone in the population. Well, this curve goes to the left forever, so it would go into negative numbers as well, but the percentages get so vanishingly small, it's still a good model to describe this, even though no one has a negative time for break reaction. That's like time travel. It also goes far, far to the right here, and there might be people who react in the 3, 4, 5 seconds range, but we just hope they don't have a license to drive potentially, because that starts to get pretty scary. The model might describe them kind of well, but hopefully they're extremely rare as well. But we did it, folks. That's the entire normal distribution. All the percentages are labeled. All the break times are also labeled here as seconds. Might not be a bad idea to add the unit here, just as a reminder, in seconds. Now we can answer questions about percentages, but we've made this connection before. Anytime a question says, what percent? That is a probability question. These could all be probabilities if we put in 0.34 instead of 34%. So the word percent and probability is fully synonymous. It's just which unit you decide to emphasize, the percentage or the decimal number. So just to make that connection again, you could have said, or probability. This came up when we were looking into those contingency tables or two-way tables. So we've got the whole entire model down. We have the parameters as well. And here are what the follow-up questions are going to look like. First question asks, now that we are modeling an entire population, let's just say, just for the sake of making it fun, this is a population of drivers in Idaho Falls, even though that wasn't the case with the real data. Supposing it was, they're asking us, what percent of the reaction times for drivers in Idaho Falls are predicted to be between 1.73 seconds and 2.57 seconds? Well, there's a definite process to make this happen. Notice the units being mentioned. We put the unit down here as well. So it's talking about information on the y-axis. And this is a weird step to take because this isn't something you can easily do on the notes. But I'm going to screenshot this right here, just so that for the sake of the notes, we can see how the information goes together. Let me try again. I didn't put the red dot in a good spot. So about right here, we'll describe how we get all of the information, the follow-up problems. Okay, so we're looking at this one for now, since it's the bigger one. Let's focus on that thing there. If we want to find the percentages, those are the portions that are above the graph, under the curve, arrows helping out. And when it says between 1.73 and 2.57, first thing we want to do is identify those numbers, 1.73, 2.57. We're going through this extent here. Once we've made that identification, all we now do is take all these percentages that correspond. So starting at 1.73 from here to here, that was the 13.5. Then we went from 2.15 to 2.57 here to here. That was the 2.35. We didn't take the 0.15. That's kind of hard to see unless I shade this a little bit better. We didn't take the 0.15 because the area we're taking just goes from here to here. That's kind of hard to highlight. Let me change that up a little bit. In other words, we're not going beyond 2.57 seconds. So we just add those two probabilities together, 13.5 plus 2.35, and that's the entire answer to the question. Looks like that's going to be 4.5, carry the 1, well, hang on, not quite 60%, 2.35 plus 13.5 comes out as 15.85%. So 15.85% of the population is going to have a breaking time between 1.73 seconds, 2.57 seconds. That's if the model is really accurate. And that's if our approximated values of the parameters are both accurate at the same time. So if this is fully accurate or very close to accurate, that's kind of a scary assessment when you think about it, right? If you hit a brake, maybe there's a cat in front of you, or maybe you just notice a road hazard. A random person in the population is going to brake between 1.73, 2.57 seconds, close to 16% of the time. And that's probably a collision. That's an eternity if you're braking hard. Well, any questions at all, folks, on how we grab those numbers? Okay, just for the sake of leaving a paper trail in the notes and not making this problem too busy, makes it hard to look at. Let's put that same information down here. We're going from 1.73 to 2.15. So that means from here to here, and all we did was grab those two percentages. So that's pretty much the name of the game. You correspond to information on the horizontal axis, grab the percentages, that's the percent of the population in that region, and it'll fully answer the question. So let's try it out again. This time it says, let me hide party here. About what percent of the reaction times are predicted to be below 0.89 seconds? So these are people who are going to respond really, really fast. Maybe they had a lot of coffee. Maybe they're anxious people. Maybe they're in driver's ed, so they're just ready to brake. Once you see this 0.89 seconds, because the unit is seconds, it reminds us we're on this axis here. It's probably good to just put in at least the unit. We highlight at 0.89, and we want to take all of this area. But notice how it was written this time. This one was between two values, so we had to stop right there at 2.57 seconds. This one says below, and it said no mention of stopping. Sure, it would stop at 0 seconds, but that's clear out here on the model. So this time, we're going from here way out to here, and we take all three of those numbers. Does that make sense on this one here, how it changed? Awesome. So all we're doing is corresponding from the information in the problem to the percentages in the model. So now it's 0.15 plus 2.35 plus 13.5. These all come in as percentages. We pretty much have it in the calculator. It's just missing the 0.15. So go plus 0.15. And that's the 16% we would get. So 16% of the population has a braking time below 0.89 seconds. And almost 16% of the population brakes between these two times, 1.73, 2.57 seconds. So this is the typical problem where we're just looking for areas, we're calling them percentages under the curve, the normal model curve. The slightly different problem would look like this one, part E. It's backwards in a real sense. So the last question was talking about reaction times below 0.89 seconds. So they're automatically talking about the horizontal axis when they gave us that unit. But this time, there is no mention of the braking time in seconds whatsoever. This is an inverse problem. So what that means is for this problem, we have to look into what we mean by the context. This was seconds reacting to a brake signal. It says describe the reaction time for the slowest reacting. Now, slowest reacting could either be on the left or it could be on the right. It just depends on the context. Anyone see what slowest reacting would mean for this context? Is it towards the right or towards the left? Absolutely. Slow reacting means taking more time to react to the brake signal. And notice that's kind of uncomfortable. If you change this context, sometimes that can be pretty vague. It might be up to the expectations of the person. If we say best or worst, well, worst should be taking too long to brake, right? But if you change that context a little bit, it might be kind of vague what best or worst means, or what slowest and fastest means. But here, I absolutely agree. Slowest reaction time means just taking longer to react to the brake signal. So this means longer braking times. So we're somewhere over here that we're looking for. What we're looking for, better said, is somewhere over here. But we've got to total up to 16%. So here's how we're going to start. We're looking for reaction times for the very slowest reacting drivers. We're starting on the upper end, the longer times. We'll take this percentage for the first region right here, but we need to total up to 16%. So that's not quite enough. So we go even further to the left. At 2.15, we're now pulling in that percentage, so add it to the calculator, plus 2.35. We're now at 2.5%. We've got to hit 16%, so 2.15 seconds is not the cutoff. We keep going to the left until we actually hit our cutoff of 16%. But now we're on this region, we're pulling in the 13.5 as well. So we have three values we tally, add 13.5. Actually, I think circling those is making this a little too busy. Let me take that off. We're now up to 16%. So the total of all these three sums to 16%. We just need to state the value then. Trying to pick a color that's going to stand out here. Just about used all my colors here. Let's go with, how about purple? Why not? Anyone see what the right value to pick would be out of this chart so far? We want a reaction time that describes the slowest reacting 16%. But we want only one time, which is kind of strange.
You wouldn't say like they're between.
Yeah, we won't want to say between. We just want one number as a cutoff. So what number would you say is best to cut off the upper 16% of all of these reaction times? Sorry, say again?
The highest one that's highlighted, right? For 1.73.
Yeah, this one right here. So this one, right at 1.73 seconds, if you react longer than that, and we add up all these percentages, that's the slowest reacting 16% of the population. So this is the one that does it. I mean, there's infinitely many other reaction times in here, all bigger, but that's the boundary value that describes the cutoff. So we can say, to answer this question, a reaction time of 1.73 seconds or longer describes the slowest 16%. I'm going to put a box on this answer because everything else we put on there was just the discussion to think about it logically. The end answer that we're trying to hit was the 1.73 seconds. Making it a pretty tricky question. There's problems just like this in MyStats lab. That's the value that they would be going for this kind of question. So in a real sense, it's the reversal of this one. This one was just 0.89 and lower is the 16% fastest reacting drivers, we could have said, if we turned all this information around. But they gave us the information backwards. They didn't give us the 1.73. They gave us the percentage or the probability, we could say, in other words. So we had to reverse engineer it and get the seconds after having the percentage.
That was a question on an exam, and you just wrote 1.73 seconds and gave full credit.
I would, yeah. It does convey, well, it does seem to miss something because you might have said or longer or shorter, but I would say it does convey the full answer to this kind of problem. So if you did short it up to just that, I would think that you're assuming this part right here. I think I would give full credit. Other questions so far? Okay. It's tricky because there's a lot going on. When you look at this diagram, there is kind of an overwhelming amount of information. The best way to track through this problem is try to focus on one element at a time. One element is either the horizontal axis with, again, 6 numbers, so 7 numbers, so that is a lot. Another element are the percentages with a bunch of numbers as well. But try to zero in on, is the question about the horizontal axis getting a percentage, or is the question about a percentage getting a number on the horizontal axis? And you can cut through all the fog of this huge amount of information just staring at us. So we'll try it out one more time because just doing one problem is not very helpful for the homework with so much going on. Any last questions at all before we try it all over again? Okay, so next problem is our redo of this whole thing. The new context, this one's fully made up, but it has some elements of drama in it, so it's kind of fun to imagine this is a real corporate setting somehow. We're told a company's manufacturing process uses 500 gallons of water at a time. So maybe you're imagining Simplot out in Chubbuck or something like that, if that's still Simplot. We're told next, a scrubbing machine then removes most of a chemical pollutant before pumping the water into a nearby lake. Idaho has really interesting laws about this kind of stuff, so this is a relevant problem. And we're told legally the treated water should contain no more than 80 parts per million of the chemical. Maybe it's something like elemental mercury. We're not sure what it is, but imagine something that's probably not good for the local flora fauna. So we need to cap out at 80 parts per million of this water that was treated. But in reality, when we do this, the machine starts out nice, and over time things wear down. Maybe it's misconfigured. So anything could happen over the course of doing this month after month, year after year, decade after decade. And they admit the machine isn't perfect. It's costly to operate. That's an interesting statement to throw into the mix. And so you have to check up on this process often to make sure everything is within spec. If they're really containing no more than 80 parts per million. So there's a whole cottage industry of inspectors that do this kind of work on a regular basis for industry. It says here, there's a fine if the discharged water exceeds the legal maximum, 80 parts per million. And so the company, aware of this, is going to take their machine that scrubs out the chemical pollutant and try to make sure they're always, or most of the time, remember, it isn't perfect, they want to be most of the time below 80 parts per million. And it's costly to operate. So the company is working between a couple things. They need to make revenue and they need to avoid legal fines all at the same time. Somewhere in the middle, they're going to set their machine to try to thread the needle on this. The company sets the machine to obtain an average of 70 parts per million of the batches of water treated. And you know that sounds good on the surface, right? If the average is 75 parts per million, it's below 80 parts per million. And if you haven't taken statistics, you might have said, that's terrific. But there's a mantra that needs to always be repeated in statistics. We've said it at least 5 or 6 times. When it comes to quantitative data, the mean or the average is never, ever the whole story. You have to take the average together with the standard deviation. Usually you use blue for average. This is interesting language. They say, they believe, maybe from routine testing, the machine's output can be described by a normal model, that's nice, with a standard deviation of 4.2 parts per million. That's the second half of the story. We're trying to be below 80 parts per million, and things look good with the average being 75 parts per million. But that standard deviation, we need to just assess, is that large or is that just fine? How often would they be fine, in other words? So we're going to figure all this out by modeling this whole population through the normal distribution with these 2 specific parameters. So that's the context of this problem here. First thing we want to do is state the value of the parameters. Using appropriate symbols for each parameter just means there are 2 parameters we're labeling. There is a mu. That's literally described as a population average. They could have said a mean of 75 or average of 75, but it's going to be this value here. At the same time, when they say standard deviation, you might say S, but recall that's the standard deviation for a sample of data. We're doing something different. We're modeling the output, the amount of pollutant in parts per million, using a model where we're assuming a value for the population's standard deviation, and that's going to be the sigma value. So sigma is 4.2 parts per million, and the mean mu is 7.5 parts per million. Forgot to get that unit in there. You know what? We can just let that one unit over here count for both. They would always have the same exact unit. So first thing we want to do is draw this normal model, see how things fit together, and then go from there. Any questions on getting the parameters out of the context? Okay, so next thing we'll do, draw down an extended horizontal axis. And you definitely want to give it a unit. If you left this off, I wouldn't take credit off of that, but it'll help us address each of the questions, because putting a unit on this axis describing the quantitative variable helps us make sense, head or tails, of what the questions are even asking. So this is 75 parts per million. We'll go over here and just say that this is also parts per million, ppm. You know what? We should say that at some point on this document, right? ppm is an acronym for parts per million. I think that this was an exam question. That could be a point of confusion. That should be written in at some point. So ppm, parts per million of the pollutant. And let's see, removes a chemical pollutant before pumping water into a nearby lake. It's from 500 gallons of water at a time. Let's just say parts per million pollutant for each 500 gallon batch. So that's what our unit would be on this problem.
What did you say? My initial thought was just kind of label it parts per million of the chemical.
I would say that'd be totally fine as well. Parts per million of just the chemical would convey that same kind of information. This one's starting to get kind of super specific with the context, but really anything that just reminds you of what that full context is that we wrote down, that would do just fine. Other questions so far? Okay, now we practice our artistry skill, write down a normal model. Here's mine. It's not doing great, but it'll do the job. Usually you want to go a little bit further on the left because 3 standard deviations is quite far, a little bit further on the right. If we were to describe this in symbols, we would say that this is n, because it's a normal model or a normal distribution. We would say the center is at 75, so that'd be the first value we put here, the value for mu, comma, 4.2, the standard deviation. You don't have to put in that notation, but it actually helps out a little bit in the next section with importing data into the calculator when we try to do this more exactly. All of our percentages are approximations because this rule itself is an approximation as well. At this point, we start to calculate. The dead on center here corresponding to the main peak is 75. Let's put in the tick marks next, so we just have them all in order as we go. About right here is 1 standard deviation, and then 2 and 3. This would be -1, -2, -3 standard deviations. Then just start typing things in the calculator. Take your 75. We're going to add the 4.2. And we'll do it repeatedly. I'll just show the one arrow so it doesn't get too busy. Going this way, we'll subtract the 4.2 from the 75 or whatever the prior value happened to be and do that one repeatedly. So I'll do the adding part first, 75 plus 4.2. I'm at 79.2. 4.2 again. You're at 83.4 at that point. And then it's kind of nice to do this. Just keep on pressing plus. It'll add your prior answer. Plus 4.2 once more. You'll get 87.6, and we're all set. Just make sure if you use this trick, everything is correct on the first line, or else it's like a game of telephone where everything is inaccurate afterwards. Then going on the left direction, type in 75 again. Now using the minus sign, minus 4.2. We get a value of 70.8 going right here. Minus 4.2 again takes us to 66.6, so fun number. Minus 4.2 again. And we're at 62.4 parts per million of the chemical pollutant. 62.4. That's way on the low end, so it's kind of nice. But notice we said no more than 80 parts per million. That's when legal fines could start to occur. And there's some actual area here. You know what's unfortunate about this model? What example 3 kind of leads into is that it would be nice if that was exactly 80, right? Because that's the benchmark where they're getting into legal trouble. But we can't force that. The rule is very specific. It's using the standard deviations, 1, 2, 3 standard deviations, and so on. So we just have to live with this is not exactly where the legal value is. Part of the reason we're going to do this in the calculator is just to overcome that problem right there. We would like to calculate the percent above 79.2. We just can't, not by this rule, not yet. But nonetheless, we can still give a decent approximation. 79.2 is close to 80. And we know in these two regions, it goes 34%, 34% again. Then finally in this region right here, 13.5%. And I have to use the arrows trick at the next one. 2.35%. Next arrow is 0.15%. Then mirroring, put the same values going to the left. 13.5% barely fits, and I thought I was drawing this big. 2.35%. And 0.15%. So finally, it's all in. This is a lot of stuff to put in. Again, the thing that's challenging about this problem is visually, this is like a forest of information. Any questions at all, folks, getting it down to this point, the model itself? Okay. Well, next question says, what amount of the chemical pollutant? This right here is a horizontal axis question. In other words, once we find the value on the horizontal axis, we're totally done with this problem here. It says, describes the 2.5% of cases for which the water is the cleanest. Well, because we're talking about a pollutant, cleaner means lower parts per million. That means the word cleanest here means we're on the lower end. But if we just threw down the numbers, 75, 4.2, built it up like this and never thought about the context, notice that would have been really, really vague. The cleanest depends on what you mean through the context itself, the fact that we're talking about a pollutant in the problem. So we're looking at the lower end. We want 2.5%. Let me just fix this highlighter. There we go. 2.5%. And here's how we would start. We accumulate from here. We're at 0.15%, so that's clearly not enough. So we go a little bit further, all the way up to this point here. Just double checking in the calculator. That would take these two percentages together, 0.15 plus 2.35. That goes to 2.5 as a percentage. And so just like in the last problem, the cutoff is the number 66.6. So we grab this number here. So we can say 66.6 parts per million or lower describes the 2.5% of cleanest cases. Really, the major thing that we want to put in is just the 66.6 parts per million. Everything else, informationally, was just trying to get us to organize and get to that number. Does that make sense to folks on how we got that value there by the red dot? Okay. Well, part D is like the question we would want to answer, thinking of all this context. There's a fine if the discharge of water exceeds the legal maximum. The legal maximum was 80 parts per million of the chemical. And so this question is doing the best it can. It's asking, what percent of the time are we going to have this company put out a batch that would lead to a legal fine? Well, we tried though, but it's not quite at 80 parts per million. We're just getting as close to it as we can based off this chart here. So that's kind of the thought to what's going on with this problem right here. We couldn't word it that way specifically because this rule has its major downsides. All questions that we ask and answer have to be to this strict scale that we put down on the horizontal axis. But nonetheless, we can still give it a shot. Here's what it would look like. I'm going to use this color just as a temporary highlighting, so our diagram doesn't get too busy, or it's impossible to read on the notes. So more than 79.2 parts per million means we're in this region. And it just said strictly more than. It didn't say between any values. So that means we would be grabbing these quantities. All three of those percentages there would begin at the 79.2 cutoff. The 13.5, we move to the right, grab the 2.35, and then the 0.15 again. So this one would be 13.5 plus 2.35 plus 0.15. You know, that kind of feels like deja vu. I believe that came out to 16% exactly for that figure there. Does that make sense to folks on getting those percentages?
Yeah, pretty straightforward.
Awesome. I'm glad to hear that. Really, the major trick to knowing that we did it in this direction was it mentioned the unit. We wrote it in. So we knew we were grabbing information off the horizontal axis. It's these parts right here. When they gave you a percentage that it's all backwards, and it feels like it might be a little bit more confusing going in that direction. But that's another one down. And this roughly tells us that the company 16% of the time is exceeding the legal maximum limit. Well, approximately. That wasn't the exact figure. This rule is an approximation. Those parameters were also approximated, and we don't even see the sample data to decide how reasonable was the normal model. It could have been just roughly symmetric or borderline skewed strongly, who knows? So there's like 4 or 5 levels of approximations that come down to this. If we can at least make this more exact, we're starting to clean up the information bit by bit. So that's the purpose of section 5.4, doing this now in the calculator. Just for the sake of trying this one more time, here's how the next question goes. What percent of batches have between 70.8, 87.6 parts per million? Well, 70.8, that goes way over here on the left. We'd begin on this region. And this is a between problem. We go up to 87.6, which means we're grabbing just those percentages circled here. So starting at 70.8, add the percentages as you go look above on the red dot as it moves left to right, but stopping at 87.6. That's why we wouldn't include the 0.15. So this would be 34% plus 34%, or 68% is a good shortcut there, plus 13.5% plus 2.35%. This would then be equal to, let's check this out. So I'll add the first two, 68% plus 13.5 plus 2.35, and we get 83.85%. Part E was just for the sake of trying this out one more time. I don't know why this would be an interesting computation based on the context, but that's a process of getting these percentages out based on the model we see above. Well, we did it, folks. This is the rundown on how to use the empirical rule. The most important thing about it is thinking in terms of this normal curve and areas under the curve expressed as percentages. Those are going to be the main things that we're going to work on in the very next section. Well, any last questions at all before we take a peek into that next section with our 9 minutes of time? Okay, let me close this out. And here's what the next section is going to look like. We're not going to try to make a huge amount of segue into it, but just mostly look into what we're trying to achieve here. First thing I did was just inherited the empirical rule, the 689599.7 rule from the prior section, 5.3. So here's that normal model again with all those percentages laid out. But if you've taken a good amount of algebra, some people have taken intermediate algebra, some people have even taken pre-calculus when they take this class, you might know that there should be an equation, a formula that describes this curve. It's not just some random thing we jot down. There's a formula for this thing. And that's the formula. It's kind of rough as far as formulas go. There's lots of things going on with it, but if you need an equation to build that curve, there it is. That's something you could put into a calculator and work with. And notice the two important elements of that equation. The mean of this distribution is the parameter mu, the mean of the population. The standard deviation that we use to express how spread out it is sigma, the population standard deviation. I'll write in pop for population standard deviation, and mu is the population mean, or you could say average. And the formula for actually building this curve uses both parameters. The mean, kind of have to really blow this up to see it, is in one spot right there, where it goes x minus mu squared. And the standard deviation shows up here, shows up here. The keen item, notice pi makes a return to this, 3.14 approximately. That is a really random fact, but there it is. That number is even worse. Pi is an irrational number, 3.14. E, that's a number you could put in your calculator. In fact, let's do it because it's a mysterious thing to even look at. E is right there under the natural log key. If you hit second and then press the natural log key, you get E. Put in a 1, and e power 1 is just E. And that's the number. It's about 2.71. Let me just admit there are approximations. 2.71. So that's some weird stuff. There's a negative sign there. Just to be straightforward with you, the formula is really more for our curiosity's sake. You're not going to be expected to use this formula directly. But I feel like if we never said what it was, it makes this curve more mysterious than it really needs to be. So it's for informational purposes. It won't be on homework, quizzes, nor exams. It's just part of the notes. And one reason I put it down is we do want to graph this curve. Here's the graph. I just imported this curve into Desmos calculator. This is only for the sake of a classroom demonstration. I won't ask you to do this for homework, quizzes, exams. That's kind of cool to know. You can just plot these things out. Here's what it would look like. And what we're going to explore next time is, what are these parameters actually doing? How is it going to affect the shape if we go from 0 and 1? What will happen if we go from -2, 1? If we blow up sigma to 10, it's good to know exactly what these parameters are actually doing in the curve, but here's the short of it. If I go to a 1, this is now the standard normal distribution. It looks kind of funny, but that's just because the axis is set in a weird way. Let's go to a maximum value of, how about 1, and a minimum value of maybe negative 0.5. And these are the curves that we've been drawing. Notice how rapidly it approaches the x-axis. Around 4 standard deviations, it's not 0. The second coordinate is 0.0005. That's the height of the curve around 3.5 standard deviations, 3.63 to the left. Now, sigma is our parameter that represents the spread of the population. If it was S, the sample standard deviation, that was a spread statistic. And if we make this smaller, notice what happens. The shape changes. The smaller the value of sigma, the more your population is accumulating to wherever the mean is. I could put in the letter mu, so I put in M. If you move mu around, all this does is just put where the center is going to be. So this is going to be the spread. It literally shows you how spread out the area is, whereas this is going to be where the center is. So we'll look at a few shapes, just getting used to seeing this from a different side. Then we'll go to the calculator and actually calculate these percentages more exactly. And we could put anything we want in the problem. Like in the last one, we could put in 80 parts per million, but in this section we can. So we can calculate things a little bit more exactly. So that's what we'll take a look at on Thursday when we come back. But any last questions at the moment before we call it a night? Okay, I don't think we want to try to cram in a bunch of graphs at the last 2 minutes of time. So this will be our stopping point. If you have any questions, I'll be happy to help out. Otherwise, we'll return on Thursday and see what's going on with the calculator side of doing the same kind of stuff. The questions are essentially the same. The tool is different, basically. But have a great night, folks. I'll see you all next time. Thank you.
Thank you. Quick question now.
Sure. Oh, dang it.
Yeah,
Yeah.
so with the quiz for,
Mhm.
if we turn it in, wait, what does it do? I know it's due tomorrow, but is it before class or after?
You know, I put a time in that's like 7:30 just because Canvas wants a time. But if you gave it to me afterwards, that'd be just fine. Pretty much if you turn it in on the day it's due, it's considered fully on time.
Okay. And anything after is deducted from,
I actually don't have a late policy on quizzes either. I do accept my quizzes late.
okay,
So if anything weird happens, maybe you had your quiz and you forgot it and you never turned it in and it's like Friday, you could still take a picture of it, send it in to me for full credit. Yeah, so I don't have any late policies whatsoever. Due dates are still important because it's just pacing, keeping caught up with the class.
yeah. Because I mean, I got speech tomorrow, like I worked on it all day today.
I gotta admit to you, I hated that class. I took it as a senior. I delayed it as long as possible, so I totally understand.
It's a nightmare. I mean, it's a topic I know about, but it's just, I
Mhm.
can't go off of my own knowledge. I have to go off of other people's, like,
Yeah,
people who are like actually, like, have made their profession off of research.
right.
And like, not to use their exact words instead of my own, so.
You know what I did for that process was I went to Wikipedia. I know that sounds bad, but then Wikipedia lists sources. So I went into Wikipedia to learn about the topic. Then I went into the sources and just made sure they said what I needed to say, and I cited those sources. So you can kind of use that as a resource.
Yeah, I mean, I already have my sources, lined up. It's just 3 for each body paragraph,
I see.
So-
Awesome.
but it's just. There's like a certain structure you have to follow and.
Yeah, it's weird, right?
I'm just not used to that because there's always more to what I'm talking about, because there's like a deeper scientific, reason behind
Mhm.
what I'm talking about, but.
Yeah.
It's just a basic informative piece
it's gotta be probably between like 5 and 7 minutes, right? So you
Yeah.
you can't even say what you really wanna say. It's like being on the news.
Yeah.
You always watch people getting cut off when they're about to make their point.
Yeah, so, and, yeah, I didn't really have enough, so my topic is creatine monohydrate,
Oh, cool.
and so a lot of it is dealing with water retention,
Mhm.
because you have to keep up with adequate, water intake so that you don't experience like muscle cramps or,
Yeah,
digestive issues, so I didn't get to that part, because also focus on the other benefits, such as like, increase, muscle recovery that can lead to better strength.
yeah.
And then as well as cognitive function, because you have more,
I didn't know about that one. That's cool.
yeah, so it's just like, there's, I can't do much of this
Yeah.
with that topic, but anyway, I'll plan on doing all the homework in this class and the quiz Friday or Saturday, because.
That would work out just fine. Yeah. College is all about putting out the biggest fire first and then focusing on other things when you have the time. So yeah, that'd work out just fine.
Well, thank you very much.
Yep, you bet.